Welcome everyone to the Agritecture's Urban Farming and Differentiating Products and Innovation in Controlled Environment Agriculture. We are hosting this webinar to demonstrate some very unique innovations in the CEA industry, both on the crop side and the technology side that enables new crops to be grown, as well as in wider areas and into different businesses. So, in addition to myself, who is the Client Success Manager for Agritecture, we have guest presenters from New Growing System, Donald Gartland, who is the Head of Business Development, as well as the Chief Scientific Officer from Hydrosome Labs, Nick Jackowetz. They will both be giving short presentations today, but first we will have Alberto Lopez, Agritecture's own systems engineer, who will be starting us off. I'd like everyone to please keep your questions to the end. We have time to discuss any of the topics, questions that you might have. So you can either post them in the chat or wait until we've gotten to the Q&A section. So with that, I will pass the microphone over to Alberto and he can begin the presentation.
Thank you, Luke. Yeah, let's get into the agenda for today. So I will start with a brief introduction, let's say, to the webinar topics, mainly focus in the diverse crops that are currently grown in CEA, and then the type of irrigation technologies available in the market. We will then move into Donald's presentation about NGS innovative growing systems and some cases of relevant crops that can be grown in those systems as well. I listed also some of the common issues that we are currently facing in the irrigation, from the irrigation perspective. And yeah, that's just for you to keep in mind, because some of this can also be tackled in combination with the solution that Nick is introducing as well. So yeah, we understand that if we manage to optimally control the environment around the plant, so virtually any crop can be grown in CEA. Next slide. Look. However, there are some key constraints that make certain crops more feasible than others. For example, we see the capital costs for, let's say for an example, a highly technified greenhouse can go around $600 per square meter. That's around $60 per square foot. And if we're talking about vertical farming systems, they can go up to $4,000 per square meter. That's $400 per square foot. So that's based on the scale. Well, depending on the scale, that's a significant investment. So then we move into the operational costs that are mainly electricity and labor, and also the difficulty of finding the right people to run the facility. That's has been a problem for many companies, especially in the vertical farming system, to scale up as well, or to create the diverse, let's say, operations. Well, in the bottom of the slide, I listed some success factors for CEA, mainly involving location and market. So you see that geography plays a big role. So yeah, what's from the operation to the markets, what's the actual distance? And then we move into the actual market conditions. So yeah, how much it will cost you for labor, electricity, water inputs. Then yeah, how susceptible the market is for the disruption of the air exports, and what is the local competition there. And also a key let's say, a factor of success is the willingness to pay of the consumer as well. Are they willing to pay high value for pesticide-free crops, for, I don't know, additional freshness, locally produced? This type of factors, will create success in the operation. Next slide. There's a good way to start is just seeing the actual drivers for CEA based on the region, right? So I listed some on the left. If there's water scarcity, if there's an involvement in food safety. So basically, if the objective of the production of food will tackle the environmental, the social, or the economic problems of that specific region. Next slides, please. Look. Now that we seen So based on the previous slides, these are the most common crops that are considered in CEA. So this is data from 2021. It hasn't changed that much. We have that from the greenhouse perspective. We have the most common are the leafy greens, the vine vegetables, berries, and also herbs and microgreens as well. And if we move more into vertical farming, we see a lot of focus in high volume leafy greens, microgreens, and herbs. And we have seen also some efforts made in berries and dwarf tomatoes. Yeah, Donald will elaborate a bit more later in some specific cases, and so also not so common crops that are grown in greenhouses as well. Next slide. So yeah, now that I show you what is currently grown, I will focus more into what how it is grown. So here are some of the different subsystems of a CEA integration. So you see climate control, the cover, the processing and logistics, and the lighting control. What I want to focus in this particular webinar is in the irrigation system. Next slide. Next slide. So this is the typical recirculation system that is used in greenhouses and vertical farm as well. If you see, we start with the storage phase, which is basically all the tanks needed to hold the water for the irrigation. If we move along to the next stage, we have the mixing phase. Here is represented a mixing tank. So this can be used with a mixing loop, which will provide first oxygenation and then also provide the proper mixing to convey the nutrients to the actual growing system. This can be used, normally there are two ways of doing it. You can do it in a mixing tank or you can do it inline as well. Then we move into the next phase, which is the delivery phase, which is how the water goes into the growing system. And lastly, but very important as well of a recirculation system, we have the return phase, in which all the drain water should be coupled with a disinfection system, including sand filter, fine filter, UV filter, and go back into the disinfected water, which will, in normal systems, will be mixed with the fresh water just to provide the proper, let's say, initial conditions for the mix. If we move a bit into the hydroponic growing systems, they have all the systems that we currently know. They have the similar main components, such as the plastic plumbing, the oxygenator, the water, the nutrients. All the objective of these systems is just to convey the nutrients appropriate into the plants. So in the next slide, we have I think it's 6 different systems. Yeah, let me see a bit. I cannot see the systems because of just a moment. Okay, there it is. Yeah, so each of the systems, it has unique characteristics. It has its advantages, it has its disadvantages. So the most common systems are the NFT, the nutrient film technique system, which consists in a light film of water continuously moving through the roots of the plants. Then we have the ebb and flood system, which is interval based irrigation that allows the plant or the trays to fill and then to drain as well. And then we have the deep water culture, which is a really big volume of water in which you have floating rafts in which the plants are grown as well. So if we move a bit also into more commercially available aeroponic systems, they are starting to get used. They have the advantage of delivering very, very precise nutrition. However, due to the high pressure needed and to the increased maintenance, basically more into the clogging of the emitters, it can be very costly as well. If we're talking about precise controls, they're needed to avoid pathogens and algae, mostly in the NFT system and the event flow, since based on the nature of how they operate, that they can be some free water left on the growing surface that can promote this type of pathogens and algae. If we talk a little bit about the deep water culture, the main advantage is the stability of the system because it has a big volume of water. However, one disadvantage is the energy it takes to oxygenate properly all that amount of water. So yeah, now we're seeing a bit of development in these irrigation technologies in which we find some hybrid approaches and some combinations of these systems trying to tackle those same problems. So yeah, if we look a little bit at let's say the possibility of integrating the WIC system into the DWC system as well, so you have the WIC and you create in space of air, then you can promote proper growth with less amount of use of energy. How yeah, with this in mind and with this approaches to innovative technologies, I would let Donald explain a little bit about NGS efforts in the development of these growing systems, and also more towards the full system and into irrigation technologies developed by NGS. So Luke, yeah, Donald, if you can share screen.
Alrighty. New growing system. This is going to be just a hydroponic presentation, a new growing system. We're Spanish. Can everybody see my screen?
Yes.
There we go. Okay, we're a Spanish firm. Let me just get this out of the way here. And we've been in business for 25 years, dedicated to recirculation of hydroponics and management control, as well as greenhouse manufacturing. We come from the Prima 4 group, which is a company that has 7,000 hectares of in-house crops. And NGS has much experience in irrigation and greenhouse manufacturing, as I said. And we have a unique patented solution. We're developers also, as well as of turnkey solutions. New growing system has 5 different types of systems. One is for berries, which is for strawberries and for blueberries. And the other one's for leaf, which would be for leafy greens, baby leaf, and then head lettuce. The other one's a new hot one, which is the tropical, NGS tropical, and that's for pitaya or dragon fruit. And then the NGS produce, which is for tomatoes, cucumbers, peppers, which has been around for a while. We also have a little one, which is NGS garden, which is mini hydroponic setups for lettuce, strawberries, and then a different system for tomatoes, peppers, and cucumbers. Okay. Let me go into the strawberry, which is our biggest hit right now, strawberry lettuce and pitaya setups. And this is our system right here. So we're based on a gutter system, a recirculating gutter system. It's fully recyclable, and it's light, versatile, and durable. So this system, it's based on a steel truss, and it has a polyethylene gutter system, which lasts up to, well, many years, depending, because in some countries like South Africa, they're using it now for 12 years. Obviously, in the system, it's healthier plants, less pesticides used, and less fertilizer needed, as well as oxygenation, which, excellent growth and early ripening with the system. This is it itself. So that's the polyethylene gutter system, which comes in rolls. Every 10, 20 years, or depending on amount of the product, they can be changed or not. So, and each one is adapted to whatever crop it is. So we can cut the holes on the top, depending if it's for strawberries, if it's for tomatoes, and even include extra layers. This is the drain and irrigation system. So like Alberto said, we're based in irrigation room where we have the header with the nutrient tanks, the mixing solutions, the computer, all the injectors, and then the water is pumped out to the field. It goes into the gutter system. The plant absorbs the nutrient solution and the water needed. And then whatever's not needed, it's drained in the inferior layer of the gutter system. And then it goes through the drain pipes and back into the reservoir tank. And there, the nutrient formula is readjusted, or it can be readjusted as it's going out. So that depends on the crop, location, and several other factors. The hydroponics, obviously, you got the plant where, since it's not in deep water nor in NFT, we irrigate by impulses. So we have, through electrical conductivity, different parameters. We're checking what the plant's taking in, and then we're irrigating according to its needs. So obviously, the growth and development of that plant is going to be in optimal conditions, because it's based on what the plant needs. And this is throughout, from plantation until the end of the life. Well, the system's completely programmable. There's no waste. It's optimized, and it's environmentally friendly. The big thing are NGS, this proprietary knowledge or development that we've created. What it does, we've taken the system, and what we do is basically double production within the same area. That's our greatest advantage. So you're going to get a shorter return on investment period. You're going to fit in the correct amount of plants according to where you're putting it in, and if you're using artificial lighting or not. And then you're just going to make everything a little bit better as to phytosanitary products, airflow, etc. And then one of the advantages is we get like a 2 to 3 week earlier ripening period. This is a system right here. This would be the rotational system, and I'll show you in a minute how it works. But what it does, it has 2 different gutter rows, and then when you're working in it, one goes on top of the other. And then when it's growing, they're just all level. This system, rotational system, is based on the floor and is for tunnel growing, okay? This is the scheme right here. So to the left, you see one would be up on top of the other when you're picking or spraying. And this is also, you can put make it so a tractor fits in there. And on the right-hand side is when it's growing. And when it's going to be growing, then nobody can fit in there. So as you can see, the entire place is completely packed. Here we have up to 160,000 plants per hectare of strawberry plants. This would be the oscillating system, which is similar, but it hangs from the infrastructure, from the greenhouse infrastructure. And every other row moves up and the other one down, right? That's when you're working on it. So it's going to be at waist level. Okay, and here we can fit up to 300,000 plants without artificial lighting in countries with a lot of light, and then 180 to 220,000 plants in countries with less amount of light. If you're putting in artificial lighting, then we can fit in, let's say, up to 400,000 plants, which is an incredible amount, right? This is the diagram, right? Position 1, that's when the plants are growing. So as you can see, it's completely, there's a space at the bottom where you can walk underneath the strawberries. And then position 2 is when one row is down and the other is up. And position 3 is the opposite. And here, normal countries, we fit in 200,000 plants. Again, it depends on what you're looking for and location, as well as artificial lighting that you could put in here. The leafy greens, 2 different types, one for head lettuce, and the other one is for smaller plants, such as baby leaf, right? And I'm going to show you, because this is the simplest form of hydroponics we have. This is outdoor hydroponics, and this is for, I mean, it's really, really good for iceberg lettuces. You can fit 115,000 pieces of iceberg lettuces per hectare, and it's very labor intensive, although the labor is only used 2 times, once during picking and once during planting. So it would be the same, let's say days as it is picked, and then it's replanted. This is the 45-day cycle plant, the iceberg. So it depends on your location. Again, you can just figure out how many cycles you could get in. The good thing about this, you could plant it anywhere on sandy, bad land or whatever. And then again, we're not contaminating the soil at all. This is the development of the roots, which is, as you can see, it's optimal. It's optimal. And then again, it's organic compatible in countries where hydroponics are accepted as organic. Okay. Then the same system, we're taking it off the ground, we're putting it in greenhouses, and then we can put them in on mobile systems. By mobile systems, I mean on tabletops or something that's going to roll, or we could even leave it fixed. Depends on the space that you have and existing infrastructure or new infrastructure you're going to build. This system is also labor intense because you're going out to the countryside or to the greenhouse and you're actually manipulating on site, and you're moving the rows to get into the next row. The good thing is you're optimizing space to the maximum. So you're getting the exact, as you can see, the highest amount of plants inside a greenhouse as possible. This would be the automated system. So this system, now what we've done, it's a little bit, well, it's quite a bit more expensive, but everything's automated. Nobody's out in the countryside. Everything is planted in a harvesting area. It goes out all the way to the back, and then it comes back by gravity. So there's absolutely nobody out here in the field. Okay. And this is, well, it's programmed 20 to 35 days, depending on the time of the year and on weather conditions to come back. This would be the system itself. As you can see, there's a slope there. In the middle picture in upper, it's the slope to the right. That would make the water go through the channels much quicker, so that every piece of lettuce is getting the right amount of nutrient solution. And then, believe it or not, all of that, there's no motors there. So everything's coming in by gravity, right? And that's one system right there. This would be a diagram of the system. So in the bottom part is the planting harvesting station. And in the outer part is the greenhouse. So this can be as big as you want. And this right here holds up to 330,000 plants per hectare, as they're smaller plants usually, which can be bok choy, any type of product, which I'll show you now. And then all the people are concentrated in the harvesting area. So you have the harvesting station, which can be maybe 4 or 5 people on each side on a normal 10-hectare project, and then 2 to 4 people on the planting station. And they're planting like each table has 400 plants per minute, and then it goes back out. So this is 100% planted, and it's in 100% production all year round. Okay, that was for head lettuce. This is for baby leaf. This is the automated, fully automated system we've created for baby leaf. And we're saying fully automated because here you don't need anybody. You have the planting, which plants the tables, then germinates, it goes out, it comes back 30-35 days later, depending on, again, on the product. And then it's harvested. Those trays are washed, dried, resodded, planted, vermilite, germination, and then back out to the country. And we can have here as many hectares as you want, with maybe 1-2 people supervising everything, as everything is completely automated. This is a beautiful system to see. Anybody's welcome to see it. This would be the diagram here, which would be very similar to the other one, right? Where we're taking one row, which is on the left, for everything that's going out. It's placed at the back, and then by gravity, it comes back down. and then harvested, and then you don't see it here, but the fully automated would be putting a planting station there, which is incredible. All this is, like I said, available to see. This is a hot new item that we have, which is the pitaya or dragon fruit. It's hot because it's a very expensive item here in Spain, and now there's a big demand for it because of its taste and sweetness. Okay, we created the same thing, the hydroponics for it, and one plant fits per square meter, so we can get 10,000 plants per hectare here. And the good thing, or the innovative thing of all this, is that due to its height, you're getting the fruit the first year. So you can get actually 3 kilos of fruit the first year. So your investment, this is a first year plantation. Your investment, as you can see, is going to get, approximately 3 kilos per square meter, 30 tons per hectare the first year. And then just keep growing until it reaches maximum production. And this is like a hot item because it's very inexpensive. It's a simple version and no labor needed whatsoever. This picture on the right is the little garden station that we do. That's for lettuce or for strawberries. And then we have another one for restaurants and private personal owners, right? That is for tomatoes and all that. Turnkey projects, NGS can do any size projects. Like I said before, from seeding, planting to the most complex engineering and automation. The greenhouses, excellent greenhouses that we build, and out of the 4 different popular types of greenhouses that we build, we have the open top, which is our own proprietary greenhouse. And the rest are just what's on the market right now, right? We're certified with a European norm, although we adapt to each market depending where we're based. It's not the same thing building a greenhouse in Canada, where we know it's going to snow and it needs to hold the load, that it is in tropical areas where the problem might be the wind. And then this is a picture of our open top, which is obviously the top opens as well as the sides. We have presence in basically all the world with all our products. And I'm just going to show you a few pictures. This is just for your information. This is a strawberry rotational project that we have in Canada. I mean, in the United States, I'm sorry. Mexico strawberry projects. This is so you can see the pictures. Some are a little bit older. And then in Atlanta, Georgia, we have a lettuce project. In Florida, we have kale, collard greens, different greens that they have. Okay. And also lettuce in Mexico with Batavia, and well, we have Salanova as well. We're working with the different seed companies. And this is just Uruguay, Colombia, Panama, Bulgaria. This is the day they planted strawberries, so it was snowing. And 2 months later, they had strawberries here in a controlled environment agriculture setup. And this is the UK, which is a large strawberry company with a rotational strawberries. As you can see, the strawberries are incredible. Portugal, we have many setups. Spain, we have the different lettuce and all that. Basil in France, which is a very good product, easy. And then the one I showed you before, which is the bok choy in Spain. And then this one, for example, the dragon fruit, as you can see, this is the 2nd year crop. Look at the difference on how the pitaya is growing. Look at those flowers. This is, this is why this is such a hot item right now. And then tomatoes in Greece, Spain, all over, right? Different types of tomatoes. And in South Africa, like I said, some of these are older projects, but I mean, they're up and running. We started building fixed systems. And now, since they've grown so much, we've done the oscillating strawberry, and it's that's what we're expanding with. And Reunion Island, different projects. This is one of the largest projects we did, which is in the Middle East. and it was for lettuce and cherry tomatoes. Okay, and this was the middle of the desert, and we managed to cool down the roots. So this was an incredibly engineered project where we could actually grow with the incredible temperatures that were there. And that's it. We have a lot of videos. We have a lot of information. Anybody interested in more information, either get on, send me an email, donald@ngsystem.com, or take a look at our webpage or however. Okay, thank you very much. I'm going to pass it over to Nick.
Well, well, we have a brief item to cover before we pass to Nick. Hold on one second, Nick.
No, sorry.
Yeah, it's just a brief introduction. Thank you very much, Donald. We listed here a bit of common issues from hydroponic systems. So it comes from the algae and pathogen accumulation to the, oh, is it there? There you go. Yeah, to the actual efficiency of nutrient distribution, nutrient use, and accumulation. And it goes also into the actual building of the systems, right? About the drain locations, especially if we're talking about refurbishing buildings in vertical farms or constructing in underground spaces as well. And also the other way around, if we're talking about building in rooftop locations, what's the space used, what's the weight of the tanks. So this is just a small slide just to understand that these problems can be tackled from the design perspective, but also integrating other innovative solutions such as the ones presented by Nick in the next presentation. So go ahead, Nick.
Cool. Awesome. All right, let me just grab my presentation here. Pop that up. Great, let me just move some things around. Excellent. Are we all set there? Cool.
Great.
Okay, awesome. Well, thanks again, everybody. Thanks, Alberto. Thanks, Luke, for having me today. So my name is Nick Jackowetz. I'm the chief scientist at a company called Hydrosome Labs. We're located in the Chicagoland area in the US. And so today I want to talk to you about a bit about our technology, our novel sort of water processing technology that we've been working on for the past few years, and then talk about some different agricultural indoor ag applications that might be of interest to the folks on the call. So let's kick it off. So I think what we always talk about with water is that it's this thing, it's ubiquitous, it's all around, it's something that we drink, obviously, we use in processing, it's sort of something that we take for granted. It's something that is obviously extremely important, but, what do we know about water and what do we know about some of its more fine properties and how we can manipulate some of those things? So even in science today, we're learning more about different phases of water, different types of ice, for example, how it freezes, different geometric shapes of how the geometrical orientations of ortho and para water, how these things work. So there's a lot that we still don't know about water and some interesting phenomena that are yet to be discovered. And so that's where sort of Hydrosome's tech comes in, is we're looking at probing further and understanding water and its properties and how it can help lots of things. So we're talking about ag here, but we do things with cosmetics, we do things with fermentation, we have partners in hydration as well. So that's just one area, but we'll dive into ag here, but just a lot of interesting applications with this type of tech. So what is it? And so where technology? Well, basically it starts with any municipal tap water. And then from there, we go through a process of cleaning it up to make it ultra pure. So going through RO deionization to get that ultra pure water, which is, if you're familiar, like a 18 mega ohm water. So very pure water. And then from there, we apply, after that's all been cleaned up, we have a downstream process, which is our patented process. And what it is here is some of our patent drawings. It's, the principles behind it are something called hydrodynamic cavitation. So we have water going into our patented chamber. There's no inputs of energy. There's no gas injection. There's no heating of this. It's just finely engineered chambers where the water goes in. and principles of cavitation are happening to it. So we have a spin that's happening in there, and we have cavitation, which is a very extreme kind of force that happens with this water. So here I'm just taking the chamber now and turning it to its side. So the water comes through. We have a cavitation core that forms. We have very low pressure that happens in there, and that kind of starts to tear that water apart. Takes the gases that are dissolved in the water already, creates bubbles, and then as that cavitation core collapses, we have a very violent shockwave actually of energy that's released. So we get localized amounts of energy like 5,000 Kelvin, very high energy. So these bubbles are then collapsing and making things called ultrafine bubbles. They're also making ionized species as well too. So we're learning more about that. But that's essentially that's the principle of how our technology works, and that's sort of where we're going to start. When we think about, though, what we're making during that cavitation, that high release of energy, it's really, we're talking about two different things: a physical phenomenon, which is this formation of something called ultrafine bubbles, which we'll talk a lot about in this talk, and also some chemical changes too. So we're creating some ionized species, again, because we have this massive release of energy, causing things to be ionized, things like peroxides and radicals that are forming, some of them forming for fractions of a second, and some of them are a bit more long lasting. But we're still investigating some of those, but generally today we're going to chat about these bubbles and kind of what they are and more about them. If we think about the physical properties of a bubble, folks are familiar with buying a can of soda or carbonated water and watching that bubble of CO2 float to the top, right? That bubble could be a couple millimeters wide or so, and that bubble is governed by buoyancy. So that bubble wants to float to the top because it is of a certain size, and it wants to come out of solution because it's lighter than the density of the water that it's in. Whereas with some of these bubbles that we're talking about, these ultrafine, or some call them nano bubbles, they're on the order of nanometers. So hundreds of nanometers, maybe 50 to 500 nanometers or so. And because they're so small, they're governed by Brownian motion, which means they just kind of float around in solution, and they're not governed by buoyancy. So they're quite stable for quite long periods of time. So it's an interesting phenomena. We've tested our samples that we've made up to a year now and still find the presence of these bubbles even after 1 year's time. Also too, if we're thinking about these bubbles and the tininess, we're talking nanoscale. We're talking about things that are very, very tiny. And when we have tiny things, there's interesting phenomena that occurs. So for example, here, if you had a 1 millimeter bubble, and then you kind of corrected for that volume, but then split that bubble into many other ones of a smaller size, in this case, 100 nanometers, your surface area goes up tremendously. So what that means is you have increased areas for interaction, and you have increased, possibilities to facilitate a gas transfer. So obviously inside that bubble is gas, so it is air, but you could obviously put other types of gases into it if you so chose, and just a lot more reactivity that's possible because you have so many of these things floating around in solution. The other interesting thing too is as these bubbles get smaller, they're held together, and the theoretical pressures that are inside of them are quite dramatic. So even here, a bubble that's about 500 nanometers, which is on the larger size of what we would see, the pressure inside of that bubble is about 7 atmospheres. So it's very high. It's almost amazing that bubble can actually stay intact after all of that, but it does. And obviously, when you have something talking about gas laws, something called Henry's law, about how much gas can be dissolved into a volume, because that pressure is so high, we can increase the amount of gas that's in there. So potentially, increasing that ability to load and transfer different gases at a very high rate. So here, if we have an example of if we had pure oxygen inside that bubble, we're talking over 300 milligrams per liter of O2 that could be the concentration in that bubble. So pretty dramatic. Other thing too, on the chemical level now with these bubbles is that they are held together by hydroxyl ions. So that's these ions together kind of are holding that tremendous force together. So that's what these bubbles have. And this kind of shield of ions will depend on the pH. But if we're talking about sort of natural water or water at a native pH, call it 6 to 7, that's what will be around it. Interesting thing happens when these bubbles burst. You actually have those hydroxyl ions turning into hydroxyl radicals. So if folks are familiar with a little bit of chemistry, a radical species is very reactive, right? It's unstable in its current state, and it wants to grab electrons from somewhere else, or it wants to disrupt the structure of something else. So if you have these localized bursts of hydroxyl radicals, it's interesting what can happen, and we'll talk about some of what the cellular implications of that are, but it's a known phenomenon of these bubbles, which is quite interesting. And so with that being said, we have sort of some of the theory and the basis behind these bubbles now. Let's chat a little bit about the agricultural implications. So what we've seen so far, and we're still, again, a company of about 3 years or so and expanding, pretty rapidly right now, but we're generally seeing faster growth with the use of our water when used in different agricultural applications. So we're seeing, increased germination, propagation success, and in some cases, obviously, increased yields and amount of sellable products. So that's just switching out the waters, keeping everything else the same. We're generally seeing these benefits across our system. If we're going to start, we'll start at the beginning perhaps and talk about germination. So we've been doing a lot of germination studies and looking at how we can increase rates of germination and overall success to speed products along or get products going or have increased rates of germination where it was tougher. So here's an example of a radish seed that are in different vials. And so here I'll walk you through the experiment. We had radish seeds in our Hydrosome water, which is the HW treatment that's on the left. And then on the right, we have those radish seeds doing a pre-soak in deionized water with a little bit of bleach. And that little bit of bleach is helpful to, and is a common type of technique to help encourage germination and growth of seeds. And so if you look here, it's a little bit difficult to see, but on the right-hand picture, you see the meniscus and the water in the Hydrosome treatment. All that water has been soaked up into those seeds after about 2 hours, whereas the kind of control bleach treatment, that water is still at the top of this Eppendorf tube here. So again, we just saw this speed, this movement of water into that into these radish seeds in this case was quite fast and quite impressive. Now let's take these seeds and now let's incubate them one step further. So that's what we did. So we put them onto germination trays, and now our treatments were these pre-soaked seeds. We had 2 trays, one where we soaked the papers in deionized water, and the one on the right is where we soaked them in Hydrosome water. And this is after about a week's time, and you can see sort of the growth and the vigor of those seeds on the right-hand side versus the ones on the left. Everything else is the same, conditions are the same. We're just swapping the waters that they are sitting in. So that deionized water is just one step before we do our process of Hydrosome water. So it's not like it's a different source or there's other minerals in it. It's the exact same thing. And it's just now it's been on the right, it's been put through our process. And you can see, again, the amount of, the rooting and what the vigor of growth that we're seeing there. So it's quite dramatic. Same thing too, we've done this a lot of germination studies with different seeds, varieties, spinach here, a couple different cultivars, just showing the overall the germination rate and cumulative rates of germination with 2 different cultivars, again, showing that Hydrosome water can help kind of kickstart that much faster. Some of the understanding behind where this phenomenon was happening here. So there's a few things, like I mentioned, we have, radical species likely being formed, localized, so that it's hypothesized that can help etch into the outer layer of the seed and help increase that porosity. So we're understanding a little bit of that. Also, these bubbles are interesting because they have a hydrophobic coating and negative surface charge, and again, that high surface area. So these bubbles tend to aggregate around something like a seed coat that also has a hydrophobic coating as well. So it kind of brings them naturally right to the seed where they can do their work. And so that's what we're anticipating here, as well as some folks have done some transcriptional RNA analysis, so RNA-seq, to look at inside these seeds what's happening with these different treatments, and they've seen increases of transcription of proteins that code for aquaporins and different things that help water flow. So there's these cascades inside the cell with these water that are happening as well too, which is kind of fascinating. So jumping over now, so it's kind of getting away from germination, talking about yield improvements and fertilizer reductions. We have seen good success there, and I'll talk about some examples we've seen in cannabis and in herbs as well. So here's a study we did with a cannabis grower in Oklahoma in the US. And we started by saying, we know our water can help likely with reducing fertilizer costs. So let's try a test here where we have two different treatments, the Hydrosome treatment and again, like a DI treatment. The DI treatment was fertilized at 100% of the nutrient requirements and the Hydrosome at 50%. So already we're reducing the fertilizer by 50%, and we're seeing the yields that he was looking for here. He was making a live rosin, which is a solventless type of product from cannabis. And the outputs were the same, despite a 50% reduction in fertilizer. So that was great. After that, we said, okay, what if we increase the amount of fertilizer during the process? So we started Hydrosome at 50% and then slowly ramped it up over time. And here we saw too, to match the DI treatment again. And by doing so, we had an increase in some of these important factors. Certainly THC content is very important in the cannabis space. So we saw, over 10% increase there. But interestingly, the terpene content, which is that kind of aromatics that come along with the cannabis plant, was up over 50%. And that's an important quality metric for a lot of folks when they're buying cannabis. Certainly on the medical side too, it's very important. And this grower was saying, listen, I can now charge a higher premium for this plant and for this flower because it has these enhanced aromas and because it has this obviously extra THC as well. So that was a big thing for him. He can now boost the quality level, get more per pound for his cannabis crop versus what he could before. Similar kind of reactions and results from a grower in Massachusetts, where he's looking at propagation, having some mother plants he was trying to propagate, and noticed that he had increased success with our water, propagating some difficult strains versus just typical water that he was using before. So we're seeing some extra benefits there too. And then finally, we were looking at, a hydroponic system here, looking at some different herbs. And here we just had, same amount of fertilizer across the board, and then looked at, just root structure, overall leaf growth, quantified that, across all treatments, and just saw this increase in yield by about, 16% in this case with these kinds of crops. But definitely, we're seeing, again, enhancements in growth across the board with this kind of water. Again, everything else being the same, just swapping in this water. So again, pretty fascinating results, stuff we're still learning more about. This is a new area, new technology that hasn't been widely adopted. And so we're continuing to push the tech. Just to summarize again, we're seeing with Hydrosome this enhanced biological effect. We're thinking it's helping nutrient bioavailability and things get in, helping nutrients get into the cells better. Obviously, if they're getting in better, you don't have to put as much fertilizer into these things, and so there's cost savings there. And then we're definitely seeing, help where this water can help in maybe stressful situations for plants, where it can get them over the hump and help them grow a bit better. So lots more work to be done here, but I think we're really excited about the tech and where it's going. Just a quick bit about our company and how we operate. So our business is not to ship water or to sell you equipment. It's about a licensing or royalty deal. So we just attach our technology onto your water treatment system, and then you start operating. And from there, there's a small royalty fee that's collected based on the success, hopefully, that you're having from increased yields or increased efficiencies, that then we capture a small piece of that. And that's kind of the business model that we operate under. Our team, is diverse and has a lot of, great experience from, healthcare, finance, consumer goods. So we have a team that's definitely, been around the block before, and, our board has a lot of folks on it too, including, folks on, one of the higher ups of the New York Stock Exchange is our chairman, and, lots of folks from Nestle and big, CPG scientific companies. So we've definitely, have the right team around us, and, we're excited to keep going. Like I said, ag is an important area for us. But we also have, a pending contract with a large beverage company right now. We did a clinical study with them showing the benefits of our water helping hydration. So that'll be coming to market in 2024 likely. And we're also doing some work with some cosmetics companies as well that are coming to market later this year to help the permeation and permeability of some topical applications too. So a diverse, array of things that we're working on right now too. But obviously, the success in the literature on ag, with this type of water is pretty interesting, and there's a lot more that we're learning. And obviously, would love to chat and get in touch with folks that are interested in this technology. So again, I'm Nick, and my contact information is there. So be happy to, to chat further and see where we can help you guys. So again, thanks so much for the time, and I'll stop sharing and I'll toss it back to Alberto and Lou.
Thanks, Nick, and thanks, Donald. Excellent presentations. These topics were chosen not to represent the sum total of where we think the entire industry is going, but rather examples of very new and compelling additions to the industry that can really help change and drive growth in the entire industry. So feel free to reach out to Donald and Nick directly if you want to learn more or you want to talk to them about their technology. And always know that you can reach out to Agritecture to understand these technologies, see how the economics of incorporating them into your operation, or how you might be able to make sure you're hedging your business's success to accommodate changes in the future. So with that, I'd like to give the few minutes left on the webinar for questions. Alberto, I think you have one question that you are all queued up to answer. Is that right?
Yeah, it was and this, yeah, I guess it relates very well to my other question that I have to Nick as well. Yeah, basically the difference or what you want to try to do in the root zone is to maintain oxygen levels and to maintain good nutrition levels to growth. So it all depends on this. So both systems, the deep water culture and the NFT can provide that. We have seen efforts in the industry. I think it's called dry hydroponics. It's called Botman hydroponics as well, trying to integrate let's say oxygenation pockets in their design just to increase that type of situation. What I wanted to ask to Nick is, did you, in those experiments for the growth and the yield, did you measure the difference in oxygenation of the two solutions? Because that can also promote a bit of the differences, right?
Yeah, absolutely. It's a good question, Alberto, too. Yeah. So I believe in that one, we did not. We had the treatments, done in a similar way. The one thing I will mention, though, is around oxygen in these bubbles too, is they are effective delivery devices, we believe. However, still the bulk amount of oxygen that can be delivered will be dissolved directly into the water itself. So these bubbles, they can carry quite a bit, and we feel like they're good delivery devices to move the oxygen where it's needed. But if you do the math and talk about how much oxygen would actually be in the bubbles, it's a fraction of a percent. It's probably 0.01% of the overall dissolved oxygen is in the bubbles. The rest, 99.9%, is dissolved in the water itself. So there's still more to learn there and still more to see. But to your point, to your question, I guess, Alberto, the DO levels overall would likely be very similar across the board.
Understood. Thank you. And I have just one additional question to Donald as well about the scale of the system. So just in terms of examples, what's the smallest scale project and the biggest scale project that you have, that NGS has built or been part of?
Let's say that the smallest is 1/4 hectare, so 2,500 square meters. And the largest that we built is 13 hectares.
It's quite big. Thank you.
Very
Thank you
large.
very much.
Very large greenhouse. So there's a question that's a great segue from that, from Mohau, that asking how you power your greenhouses. Can they be used with alternative energy such as solar or a standalone generator?
We're basically powering with electrical, but I mean, there's we're working on a new project that's electrical with cogeneration and solar panels. So it's going to be our first project with that. Every other project's been off the grid up to now.
I am reading also questions for Nick here, and it's mostly about the system, the energy consumption of the system, and the volume capacity of water that can be processed.
Great question. So yeah, so we can get some of our engineers to provide some of the energy inputs, but again, there's no heating or electrical input into the system itself. It's just really pumping of water through these finely engineered chambers that we design, and then collecting it from there. So it's really not of input. And then the flow rates, like, you know, we can modulate depending on the size of the operation. For example, our water partner that's doing bottled water wants 300 gallons per minute. No problem, versus some other cannabis growers and other types of ag growers are maybe less than that. So we can take our technology, and we typically at this point put it into parallel. So we have like a chain of them all together in a row in like an array, and then we can match the flow rates based on that. So it's scalable pretty highly in that regard.
So following up on that, Nick, does the hydrosomal water change the solubility of nutrient salts in water?
We've seen increased ease of solubility of water soluble things. So a lot of our clients will say is like it was easier to dissolve, you know, certain salts or certain, again, water soluble compounds into it. Again, we think because there's more interactions, those bubbles might help facilitate, you know, better dissolution into the water. So we have seen anecdotal evidence of that because the bubbles are so small, and it's a very subtle thing. So even measuring these things can be a bit difficult at times. So we have, you know, particle tracking technology and dynamic light scattering to measure them, but it's something that's still a bit difficult, to be honest, and we're working on it. But yeah, so to your question, we definitely have seen some increases in solubility or ease of solubility.
Excellent. How about, there's a lot of questions that I'm trying to summarize them. So I'm going to summarize a few different questions into maybe one, in that, where do you see the greatest applicability for hydrosomal water in the agricultural sector? What scale and what systems will have the most benefit from it?
Yeah, that's a great question. It's something we're still looking at too right now. I think obviously crops that are of higher value, I think we can drive, if we can increase yields and we can, you know, increase the quality of those crops, then obviously we're going to get better returns there. So that's something we're looking at. That's why we kind of focused on cannabis to begin with, because of the high value of that crop versus some other commodity that doesn't have as high of a value. So definitely focusing on things that are, you know, higher value, and looking at ways to reduce fertilizer, which obviously has a cost savings, but the quality too is what we think is a big driver to increase the price of that product.
Gotcha. Okay. All right. And so let's do one more question for you, Donald. I've seen some questions about the economics of greenhouse operations. And while I know that each greenhouse has its own business model, generally, what do you see as the range for the payback period on your systems? Is there any one deployment of your technology that you see that generally has a shorter payback than others?
We're seeing, I mean, we plan on 3 to 5 years, although, you know, for example, some of the systems we put up, coincidentally, there was a hail and the demand for fruit went extremely high up, and they paid the system off in their first crop. So, but I mean, to be realistic, I'd say 3 to 4 years. 3 to 4 years.
And just one final question about for Donald. Where do you see the industry growing? Or going mostly into innovative crops, let's call it like this, for greenhouses. How do you see this developing? What do you think will be the next crop?
I mean, I think our main crops right now, what we're seeing, it has an incredible demand, is for less labor. Like I showed you with the lettuce, you know, you have the high intense, simplest hydroponics, which is outside and in the fields. But I mean, there's a lot of labor involved for big setups there. And then the automated system. Now, the thing is, the system, the simplest system, let's say, just as an average, and just like a ballpark figure is like 10 cents per hectare. Well, let's say 100 euros per hectare. And then the automated system is like 1,000 euros. So it's a big investment. It's a very big investment to make. And it's got to be, there's got to be an investment group backing it up or a big company. And right now, what the proposals that we have in North America are big companies. I mean, for the lettuce, right? Automated, as in the normal ones, we're working with small farmers. And then the strawberry setups, everybody. But going back to your question, I think, like, for example, the pitaya, that's from night to day, we just have like 6 projects going on, which are 4-5 hectares each. So it's just a big boom there.
Thank you.
Excellent. That's very interesting. So as you can tell from both these presenters, there's a common trend that no, it's not one size fits all, and that you really need to tailor almost every aspect of your operation to fit your location and your business model. And so knowing which innovations to incorporate and when to take advantage of that is a challenge in and of itself. So I would encourage everyone, if they want to speak about their project, reach out to Agritecture. You can contact me at luke@agritecture.com or Alberto at agritecture.com. I would be happy to talk about your specific projects, how we can help, or reach out to Donald and Nick directly. So with that, we're a little 3 minutes past the hour. So I want to thank everyone for attending. I hope you enjoyed the presentation. Thanks again to Donald and Nick and Alberto for presenting. And I hope everyone has a great rest of their day. Thank you.
Thank you.
Thank you very much.
Thank you.
Thank you.
Luke, Alberto, Nick.
Thanks, Donald. You too.
Bye.